This video is part of an online course of multivariable calculus, and we're going to talk about computing triple integrals in cylindrical coordinates. So assume that we want to compute the triple integral of f dv over solid S, where the solid S is like that. So let me graph it. This is y-axis, z-axis, and I have also x-axis in here. Then I have a solid like this, for example. Something like this. Okay, so this is the solid S in R3, and the projection of this solid is like that in xy plane, is something like, for example, this region here that I call it R. Assume that region R is like a polar region, which is basically the region that has a simpler description in polar. So we have a polar region, and what is description of R is all the points R and theta such that theta is between alpha and beta and R is between h1 of theta and h2 of theta. Okay, so let me graph R in a separate graph. So I have x-axis, y-axis, and then I have this one, which is basically theta equals to alpha, and then I have a ray in here for theta equals to beta. So theta is the angle from the positive x-axis. That's why we have one angle in here for alpha and another angle in here for beta. And then just assume that we have like a curve in here for h1 of theta. This is the bounds for R, and I have another one, like for example this one in here, which is called h2 of theta, and the region in here, it is R. Okay, and let me actually give you the description of S as well. So the solid S has this description: all the x, y, and z such that x and y, the first two coordinates, are in the region R that we described it in here, and then z is between h of x and y and g of x and y. Okay, so for example, the upper bound for the height would be z equals to h of x and y, and like the lower bound is g of x and y. Okay, now if I want to write this triple integral in cylindrical coordinate, I would write it like that. I'm gonna transform everything into polar. So f of, if I have x, y, and z in here, it would be r, theta, and z. And then I have the volume element in here that I'm gonna explain it, which would be dz r dr d theta. You see, it's just r dr and d theta would be like a polar, but we have an extra axis z. And then I'm gonna have the bounds for z. I know that z is between g and h. Okay, so there would be z from the bottom, which is g of x and y, and then z for top would be h of x and y, and then r You see, looking at the graph of R, I'm going to have a ray in here. The first point to hit the region, it would be h1 of theta, so I'm going to say h1 of theta, and the second point that leaves the region is lying on the h2 of theta. R actually is h2 of theta, and then theta is between alpha and beta, as you see in here. So theta is from alpha to beta. That's how we set up the integral. It's so easy. It's just one extra kind of an element just for the height, and then everything else would be exactly like the polar. So let me just give you a small note about the volume element. So the volume element dv would be equal to what? In the Cartesian, it would be dx, dy, dz. Okay, but in polar, it's something else. Why? It's just because assume that in in Cartesian, we have x, y. In cylindrical, we have what? We have this shape in here that we're gonna make it into small boxes, and for every box, let's see what we have. Okay, for example, for this box in here, we have a height which is delta z, and then we have the area of the base. So delta v would be the height times the area of the base, and the area of the base, since the base is in polar, we can write this as r delta theta, which when we take the limit, it would be dz, and then r d theta, d theta. Okay, that's how we set up the integral in cylindrical coordinate, and we often integrate with respect to z first to think about the region between a boundary on the bottom to the height for the top, and then we can think of it as we project the solid into the xy plane, and then we'll look at the shadow of this solid into the xy plane, and the solid is something that has a nice description in polar. That's why we transfer r into polar. Okay, let me give you one example to just illustrate how we can use cylindrical coordinate to makes the triple integral easier. Find the volume of the solid that is enclosed by the cone z equals to square root of x squared plus y squared, and the sphere x squared plus y squared plus z squared equals to 2. Okay, the first thing is to graph the region that is given. So I'm gonna graph y, z, and then x-axis. I have sphere, okay, of radius 2, so this is equation of the sphere. X squared plus y squared plus z squared equals to 2. And then I have a cone in here. You know how to find equation of the cone, right? So the cone would be top and bottom, but I don't have the bottom part. It's just because it's z equals to square root. That's why I don't have this part. Okay, so I want to find volume that is between these two, which is basically the thing that we have right there. I want to find the volume of this part between these two. Okay, let me show it to you the graph. Okay, so this is the cone. Z equals to square root of x squared plus y squared. It's the top half of it. It's just because z is positive, it's equal to square root. And that's sphere, and as you see, these two have intersection. Let me make the sphere hollow. Okay, now it's good to understand that what we want to find. The volume of the solid that is inside the sphere and it's above this cone. You see? Exactly the part that is inside the cone we are looking, inside the sphere and inside the cone that we are looking for. Okay. So I'm gonna set up integral in Cartesian first. In Cartesian, what do we have? The volume would be equal to the triple integral. I'm gonna put 1 for the function, and then dz, okay, and then dy dx or dx dy, whatever that's easier. So for finding the bounds for z, I noticed that if I have a parallel line to the z-axis, the first point, so let me graph it, the first point to hit the region is lying on the cone. So I'm gonna write z equals square root of x squared plus y squared as the lower bound. Let me move everything just to have more space. I'm gonna move this one a little bit on here, and then the point that on the ray that leaves the region would lie on the sphere, which is basically the top boundary. So it would be what? I'm gonna write equation of the sphere like square root of 2 minus x squared minus y squared, and it's square root because we are considering just the top part of it. So z 2 minus x squared minus y squared. Okay, and then let me find the shadow of the region into xy plane. If we are standing here and then we just basically look at the solid, what do we see? Let me graph it. X, y. We're seeing a circle, right? But what is the boundary of that circle? Think about this. We are graphing the shadow of the region in xy plane, and something that is important is the boundary of the shadow is this circle or ellipse that we see in here. You see, that's the boundary of that. And where is this? It is in the intersection of the cone and the sphere. So how can I find the intersection? I say z equals to equation of the cone. I'm gonna set both of them equal to each other, and then equation of the sphere, which is 2 minus x squared minus y squared. I'm gonna square both sides. So x squared plus y squared equals to 2 minus x squared minus y squared. I'm gonna bring x squared minus y squared on the other side, so I get 2x squared plus 2y squared equals to 2. So I get x squared plus y squared equals to 1. I skipped just one step. And that's equation of the intersection, which is, this is the boundary, and then inside this disk would be the region R, right? That's the region R. Okay, I'm gonna find the bounds for this. I'm gonna start with dy first. So I'm gonna graph a parallel line to the y-axis. This is the lower bound, this is the upper bound. So the lower bound lies on this part, which is what? Which is, I'm gonna bring x squared on the other side, and then I take a square root. So I'm gonna write y equals to negative 1 minus x squared, and then the top part would lie on the top half of the circle, which is square root of 1 minus x squared. And then I'm gonna have the bounds for dx starting at here, which is negative 1 up to 1. Negative 1 to 1 would be the boundaries for x. As you see, this equation, this triple integral is hard to calculate because we have a square roots. That's why it's better to transform it into polar. Okay, I'm sorry, into cylindrical, because we're in 3D. So in cylindrical, what do we have? I'm gonna graph the volume. Let me basically just make this one a little small so that I have more space. Okay, so the volume, I need more space, right? To be equal to the triple integral, I'm gonna put 1 dz. Okay, so the bounds for z would be exactly like here, and I'm gonna transform it into cylindrical. So this is z equals to r, that's equation of r. So z equals to r, and now transform this one into polar. So this is z equals to square root of 2 minus x squared plus y squared is r squared. So z equals to square root of 2 minus r squared, and then I have r dr d theta, equation of the circle, and transform it into polar. I'm gonna graph a ray in here. So r starts from 0 to 1. So r is from 0 to 1, and to make the full circle, theta is from 0 to 2 pi. It's much easier, right? Now let me calculate this. So I'm gonna start with the inner integral. The integral of 1 dz is just z, which is from r to square root of 2 minus r squared. So what do I have? I have the integral from 0 to 2 pi, 0 to 1, and then I'm gonna plug in this one for z. I get square root of 2 minus r squared, and then minus r, and then r dr d theta. So r dr d theta, right? So I'm gonna simplify this one. I get r square root of 2 minus r squared minus r squared. Let me calculate this integral now as over here, like in a note. I'm gonna calculate the integral from 0 to 1 of r square root of 2 minus r squared dr. Okay, I'm gonna use u sub for it. U is 2 minus r squared, so du is negative 2r dr. So I have the integral. I'm gonna multiply this by negative 2 so that I get negative 2r dr, which would be my du. So I multiplied by a negative 2, that's why I divided by a negative 2, and then square root of u, right? So I get negative 1/2, and then I get u to the power of 1/2. So it is u to the power of 3 over 2 over 3 over 2, which is what, negative 1/2. Actually, it would be the 2 here with that 2 here would be cancelled. So I left with negative 1/3 u to the power of 3 over 2, which is negative 1/3. U is 2 minus r squared. From 0 to 1. Plug in 1, I get a 1. So negative 1/3, I get a 1 minus, plug in the 0, I get 2 root 2. Okay, so I calculated this integral. So let me write the first integral, 0 to 2 pi in here, and then 0 to 1 of the square root. The answer is negative 1/3 of 1 minus 2 root 2, and then the integral of negative r squared dr would be negative r cubed over 3 from 0 to 1. Don't forget d theta. So I get 0 to 2 pi of negative 1/3 plus 2 root 2 over 3 minus 1/3 d theta. So this is negative 1/3. All of them would be just a constant, then times theta. Negative 1/3. Let me factor out the 1/3 from everything. So I get a 2 because of that. And then minus 2 root 2. And then times theta from 0 to 2 pi. So I get negative 2 pi over 3. And then 2 minus 2 root 2. Minus 2 root 2. That's the volume. Our volume is not negative, it's just because 2 root 2 is bigger than that. So I'm gonna write over here that the volume is equal to, I can factor the 2 in here, so this part is also negative. So I factor out the negative times another negative, it will be positive 2 pi over 3, and then 2 root 2 minus 2. That's the volume of the solid that is between these two.